Superposition. Ah, a theorem that usually frustrates people within circuits 1 because we just went through loop analysis and also nodal analysis, and now we're going through and taking quite a few steps in order to actually solve for the problem when we're able to do it with just a few systematic equations. So, wanted to go over a couple of problems that we had from the homework, and specifically I wanted to look at 4.13 as well as 4.15, just to kind of make sure everybody understands and gives a little bit of face time with me on how superposition is actually performed, and also some of the considerations that go along with superposition. Now, the theorem of superposition again states that basically any voltage across an element or the current through it is dependent upon and made up of the algebraic summation of all of the individual contributions from each individual source within the circuit. And so, for instance, if we have 3 sources, we turn off all sources except for one, then solve for the voltage or current with conventional methods, and then repeat that step for each other independent source, and in that case this would be 3 parts. And then we just take the algebraic summation at the very end of all of the voltages or currents. So for 4.13, I like this problem because it actually gives us not only experience into how to actually perform the superposition method, but also gives us additional experience into utilizing source transformation, which was why I didn't actually assign too many problems for that. Now, with 4.13, if we look at this problem right here, we have a current source, a voltage source, as well as another current source. And so we were looking for actually the voltage across the 5 ohm resistor. And in this problem, if we have 3 sources, then we're going to have 3 contributions to that voltage across the 5 ohm resistor. Now, once again, when we consider turning off basically a voltage source, that means that that voltage source goes to 0 volts, and we model that 0 voltage with basically a short circuit, which is nothing more than a piece of wire. When we turn off a current source, that's essentially like removing that source from the circuit, or essentially cutting the wires to it. So 0 amps means that no current can actually flow. Therefore, we model turning off a current source as an open circuit. So 0 amps means no current can flow whatsoever. Now, so once again, 3 sources. We're going to have 3 parts to this problem. Let's take a look at part 1. For part 1, I wanted to leave on the 2 amp source, but turn off the 12 volt source as well as the 4 amp source. And by doing that, we actually cause a short to be replaced for the voltage source and an open circuit for basically that 4 amp source. And so from here, if we look at, we got 2 amps that's in parallel with 10 ohms, and then we got 8 ohms that's in series with 5 ohms over here. If we go ahead and actually convert over the 2 amp source in parallel with 10 ohms into a voltage source in series with that 10 ohm resistor, then we will effectively create basically one series loop. And we can see that right here, guys. That here we would actually convert that over with 10 ohms being multiplied by 2 amps, so therefore we get 20 volts. Put that in series with 10 ohms, and that becomes now in series with 8 ohms and also 5 ohms. So all we have to do is just very simplistically go through and perform voltage division. So 20 volts, and here that would actually be 5 ohms over 5 plus 10 plus 8, and that gives us a value of 4.35 volts. And if we look at basically the original problem, we have to stay consistent with the polarity that was actually given for us for the voltage across the 5 ohm resistor at the very beginning of the problem. And in this case, current would have left the 20 volt source and then actually went into the positive terminal of that 5 ohm resistor. So that means that that voltage across that 5 ohm resistor for that contribution is in fact consistent with the way that the problem has asked. Now, let's take a look at part 2. So once again, theorem of superposition basically states in terms of a process that we have to just analyze that circuit one source at a time. So now we go back, we're going to turn on that 12 volt source and then leave off the 4 amp source, so that stays off and represented as an open circuit. And now we're going to turn off that 2 amp source. And once we turn off the 2 amp source, that is an open circuit now. And so within this single closed loop, we can easily just go ahead and perform simply voltage division. Now, here, if we go around the closed loop, now if here we represent by essentially looking at passive sign convention, current has to actually go into the positive terminal of the 5 ohm resistor. And to stay consistent with the way that that voltage was asked for at the very beginning of the problem, if we say that current flows around in a clockwise fashion, which would actually go into the positive terminal of the 5 ohm resistor, then sure enough, actually that current would actually go from the positive terminal, go into the positive terminal of the 12 volt source. Considering that, we need to go ahead and just take in consideration a negative value for basically that 12 volts. So I'm going to maneuver the camera over just a little bit. And so by taking that negative value of 12 volts, multiplying that by 5 over 5 plus 10 plus 8, then we actually take in consideration that negative value, giving us negative 2.61 volts. So our second contribution is actually a voltage that's going to be opposite of the way that the voltage was asked for in the problem. So we need to make sure that we always stay consistent with the way that the problem is asking for either the polarity of a voltage or even for the direction of a current. So let's take a look at part 3 here. So part 3, we're going to turn back on that 4 amp source. We're going to turn off the 12 volt source. We're going to short that thing out. It's just a piece of wire. Now we're going to turn off that 2 amp source. Leave that one off. Here, represented as an open circuit for a current source. So all we have left here is essentially 10 ohms in series with 5 ohms, but we can actually take 4 amps, multiply that by 8 ohms here, and take that parallel relationship of a current source with the 8 ohm resistor and convert that into essentially a series voltage source with an 8 ohm resistance. And so all we do is take 4 amps, multiply that by 8 ohms, and then we get 32 volts. And so the polarity current is actually moving in the right direction. Therefore, we put the positive terminal, once again, on the right. Put the 8 ohm resistor in series, and if we go around the closed loop, current, sure enough, leaving the positive terminal of the 32 volt source going into the positive terminal of the 5 ohm resistor, which is consistent with the way that the problem asked. And so once again, we have a single series loop here. And with that single series loop, we have V naught, 3, and that would actually be 32, multiplied by 5 over 5 plus 8 plus 10, and that gives us a value of 6.96 volts. So 3 contributions for 3 sources, and if we just kind of maneuver camera back over here, we can actually see that sure enough, 3 contributions for 3 sources. We got V naught is equal to V naught 1 plus V naught 2 plus V naught 3, which gives us 4.35 minus 2.61 plus 6.96, which gives us a final value of 8.7 volts for the total voltage across that 5 ohm resistor. And guys, if we went through and solved with loop analysis or nodal analysis, we would find, in fact, actually, that that value was equal to 8.7 volts. Now, just to reiterate that the process here that we're looking at in circuits 1 is really more of a proof of linearity to show you guys that sure enough, each voltage is basically the algebraic summation of the contributions from each source within the circuit. But as my guys in circuits 2 are already learning right now, they are actually having to deal with sources with varying frequencies that has a very, very unique effect onto those values of voltages and currents within the circuit. And so it goes from being just a proof of linearity to an absolute critical method that we have to utilize. So let's take a look at 4.15 right now and see if we can get a further understanding of how we actually perform superposition. Maneuver the camera back over here. All right. So this one was slightly more complex. than actually looking at the prior problem. So just a little bit more complex, but it gives a little bit more practice in terms of not only how to visualize the circuit when we're actually turning off sources, but also just more experience with source transformation. Now, here we were actually looking for a current instead of a voltage. So with superposition, if we consider that we have voltage source, a current source, and a voltage source, then that means we're going to have 3 contributions for 3 sources for the current through the 3 ohm resistor. So I is equal to I1 plus I2 plus I3. Let's take a look at part 1. I'm going to leave on the 20 volt source, turn off the 2 amp source, and also turn off the 16 volt source. And in this case, 16 volt source here becomes a short, the 2 amp source becomes an open circuit. So here, if we consider, once again, the polarity of the voltage source coming passive sign convention, current leaves the positive terminal of the 20 volt source, which means that the current through the 1 ohm resistor, which becomes basically in series with the 3 ohm resistor, means current is flowing within this consistent direction of the way that the current has been asked within the problem. Same thing with the 4 ohm resistor here. Current would leave positive terminal. This relationship becomes 4, essentially in parallel with 1 plus 3, which is 4. So we have 2 parallel relationships now due to the fact that that current source turned off and that voltage source is now shorted out. So 4 in parallel with 4, we got to get that source current, and so that gives us 2 ohms. And so for here, guys, we actually would have, oh, I forgot to draw this. I'm totally sorry about that. That we actually have a 2 ohm resistor down here. Make sure that I fix that. In fact, I did. Yes. Now, that 2 ohm resistor here, we get 2 that will actually become now in series with 2 ohms. So 20 volts divided by 2 plus 2, or 4, that gives us 5 amps. But that 5 amps is actually going to divide up between 2 parallel branches, both of having the same resistance. And so if they have the same resistance, then essentially that current is divided directly in half. And so 5 amps is easily rendered into 2.5 amps. So our first contribution for this problem, guys, is actually 2.5 amps. So now we need, just as we said, with superposition, repeat that step for every other source within the circuit. So once again, we're going to go back, we're going to leave all sources off except for 1, and then we're actually going to go ahead and solve once again for the current through the 3 ohm resistor. Let's maneuver the camera a little bit further to the right. Now for part 2, I wanted to short out the 20 volt source and also short out the 16 volt source, in which we're going to utilize basically our 2 amp source. Now it's pointing downwards, which means that that current would actually go in the same direction that we would be looking for, consistent with how the problem was actually asking for that current, so pointing downwards. But due to the nature of the fact that we turned off these 2 sources and looking at the nodes of the circuit, 4 ohms becomes in parallel with 2 ohms, and so that actually becomes 1.33. Here we actually have 1 ohm of resistance in parallel with a 2 amp source. The easiest way to find the current going through the 3 ohm resistor, just perform source transformation. And once we perform source transformation, we actually easily garner just simply 1 single loop. And sure enough, we get 2 volts, current source is pointing downward, therefore the positive terminal is actually going to be pointing downward too. Therefore, current leaves the positive terminal, goes into essentially the positive terminal of the resistance, giving us a current consistent with the way the problem was asked. So sure enough, 2 volts becomes in series with 1 ohm, which becomes in series with 3 ohms, which becomes in series with 1.33. All we have to do here, guys, is just simply just go around the closed loop and then apply Ohm's law. And then simply here, KVL and Ohm's law, that actually gave us a value of 0.375 amps. So for the third and final part of this problem, We're going to turn off the 2 amp source. We're going to leave on the 16 volt source and then short out the 20 volt source over on the left. And for this one, guys, this one's a little bit different. So going back to how we have to consider how current is actually flowing in the circuit based off passive sign convention, and whether or not we actually need to negate basically one of our values. Here we can easily just take a look and see that 2 ohms now becomes in parallel with 1 plus 3. These two are in series, effectively because that 2 amp source has been turned off. So here, all we have to do is find a source current, and then simply because of the parallel relationship of 2 and then the equivalence of 4 ohms, then that current will actually just split proportionally between the two. So we just find the source current and then easily utilize current division. So sure enough, 2 in parallel with 1 plus 3, or 4, gives us 1.33 ohms, gives us one single loop. Here we find IS, current's leaving out of the positive terminal at the 16 volt source. However, if that current was leaving out of the positive terminal of the 16 volt source, what happens is that once it reaches these parallel branches here, then it would actually split and go in the opposite direction of the way the current was asked for and denoted at the very beginning of the problem. So here I3 is pointing downwards, it's actually going to go upwards. So we're going to have to take a negative sign into consideration. So sure enough, here we found that the source current was equal to 3 amps. Take 3 amps and then we utilize current division. Look at the opposite resistance in the numerator, 2 over 2 plus 4, and that gives us 1 amp. But we need to make sure that we take that in consideration for the final solution for this problem. Let's take a look here. Sure enough, we consider that I is equal to I1 plus I2 plus I3, then 2.5 amps plus 0.375 minus 1 amp. We have to take that negative sign into consideration. Gives us a final value of 1.87 amps. So this should be a good review, and if you guys have any problems with these solutions for these two problems, just shoot me an email and we'll work it out together.